Have you ever asked yourself why you need to study so hard? I've heard that the scope of this final examination is all about encoding, decoding, repetition, and having codes. Have you ever got frustrated by the pressure given to you?
How could be this week so exhausting and hard? Did you already review for the final examination next week?
I've heard that the scope of this final examination is all about encoding, decoding, repetition, and having codes.
What if we'll try to do group study and help each other understand all of this? Or we couldn't do this alone. Do you guys agree?
I agree. I mean, if we'll help each other to learn and familiarize everything, it will be more easier for us. And also, this can serve as our last funding for this school year. Have you guys read the topics that I sent in the group chat last night?
Yes. And you assigned the encoding and decoding to me. So, shall we start? Okay, so let's start. Based on what I have read, encoding and decoding has a different definition in communication process, computer application, and in mathematics. In communication process, encoding means the creation of message which you want to communicate with other person. On the other hand, decoding means listener or audience of the encoded message. Example, you may realize you're hungry and encode the following message to send to your roommate. I'm hungry. Do you want to get a pizza tonight? As your roommate receives the message, they decode your communication and turn it back into thoughts to make a meaning. While in computers, encoding is a process of putting a sequence in character, like letters, numbers, punctuations, and certain symbols into a specialized format for efficient transmission or storage. Decoding is the opposite process, the conversion of an encoded format and back into the normal sequence of the characters. The example of encoding and decoding in computers is the Morse code. Next is in the mathematical literature. An encoding or coding is a mapping of an arbitrary set A into the set of finite sequences, or words, over some alphabet B, while the inverse mapping is called the decoding. And I've also read about the error and error correction. Error correction refers to the procedure of identifying and recovering error-free data from sent communications. The error correction assures that the receiver receives rectified and error-free messages. And also, there's this thing called ARQ. It means automatic repeat request. It is an error control mechanism for data transmission which uses acknowledgement or negative acknowledgements and timeouts to achieve reliable data transmission over an unreliable communication link. ARQ can also be considered as an error control or error correction.
That was interesting, and in fairness, I understand what encoding and decoding is all about already. So, who's next?
I guess it was me. The next topic was error detecting codes and repetition, right?
Definitely right, Paul.
Alright, so error detection techniques are responsible for checking whether an error has occurred or not in the frame that has been transmitted via the network. It does not take into account the number of error bits and the type of error. For error detection, the sender needs to send some additional bits along with the data bits. The receiver performs necessary checks based upon the additional redundant bits. It finds the data is free from errors. It removes the redundant bits before passing the message to the upper layers. There are three main techniques for detecting errors. Data frames. So first, priority check. Second, checksum and cyclic. Last, redundancy check or CRC. The priority check is done by adding an extra bit called priority bit to the data to make the number of first, either even or odd depending upon the type of priority. The priority check is suitable for single bit error for detection only. The two types of priority checking are even priority, where the total number of bits and the message is made even. Odd priority, here the total number of bits in the message is made odd.
The topic about Hamming code is interesting as well. In mathematical terms, Hamming codes are a class of binary linear code. For each integer r less than or equal to 2, there is a code word with block length n equals 2r minus 1 and message length k equals 2r minus r minus 1. Hence, the rate of Hamming codes is r equals k over n equals 1 minus r over 2r minus 1, which is the highest possible of codes with minimum distance of 3. Example, the minimal number of bit changes needed to go from any code word to other code word is 3, and block length 2r minus 1. The parity check matrix of Hamming code is constructed by listing all columns of length r dot r non-zero, which means that the dual code of the Hamming code is the shortened Hadamard code. The parity check matrix has the property that any two columns are pairwise linearly independent. Due to the limited redundancy that Hamming codes add to the data, they can only detect and correct errors when the error rate is low. This is the case in computer memory, usually ROM, where bit errors are extremely rare and the Hamming codes are widely used. And a ROM with this correction system is a ECC ROM or ECC memory. Example is used in the Bell Telefono laboratory error phone punch carrot reader to detect the error and correct them. Hamming developed technique for detecting and correcting single-bit errors in transmitted data.
I don't know, but Hamming code got my attention as well. So, I will be discussing the examples. Example, problem number 1. Encode a binary word 11001 into the even parity Hamming code. Given, number of data bits, n equals 5. To find the number of redundant bits, let us try p equals 4. 2/4 is greater than 5 plus 4 plus 1. The equation is satisfied and so 4 redundant bits are selected. So total code bit equals n plus p equals 9. The redundant bits are placed at bit positions 1, 2, 4, and 8. Construct the bit location table. To determine the parity bits, for P1, bit locations 3, 5, 7, and 9 have 3 1s. To have even parity, P1 must be 1. For P2, bit locations 3, 6, 7 have 2 1s. To have even parity, P2 must be 0. For P3, bit locations 5, 6, 7 have 1s. To have even parity, P3 must be 1. For P4, bit locations 8, 9 have 1s. To have even parity, P2 must be 1. Thus, the encoded 9-bit Hamming code is 1110011101.
Hopefully, you'll get interested all the timer, Leo. Okay, it's my turn. When we say repetition code, the repetition code is one of the most basic error-correcting codes in encoding theory. The aim of the repetition code is to simply repeat the message numerous times in order to transmit a message over a noisy channel that may contaminate the transmission in a few spots. The hope is that just a small percentage of these repeats are corrupted by the channel. Because the received data stream does not repeat a single message, the receiver will detect a transmission error and the receiver can recover the original message by looking at the received message in the data stream that occurs most frequently. The formula for the k is given k is equal to 2r plus 1. So the given r is 3 plus 1 over there and plus 1. So our k is 2 times 3 is equal to 6 plus 1 and the result for our case is 7. If you're already done computing the k, our source message which is 101, we have to repeat it depending to the equivalent of the k. So it will be 101, 101, 101, 101, 101, 101, 101. So we have 7, 101. And that is our final answer. Why is it 7? Because it is the result when compute the k, so we need to repeat the source message which is 101 into 7 repetitions.